Okay. I want to start with apologies to those younger mathematicians who are. By the way, Angel told me that all this colloquy is organized actually for you, so to say. And so I want to apologize because I am already, my Spanish is still awful, but I am already teaching Spanish. But before each lecture, it takes a lot of time to learn actually what are symbols, should I pronounce, how should I call them. And I could not do that to this seminar, so I apologize for that, and I will give this seminar in English. But if you have some problems with English, as it happens very often, so you can actually ask me questions in Spanish. I will be happy to. I hope that I will understand your questions in Spanish, and I will definitely answer. Now, why I want to give this talk first, and why about this topic, particular topic? In brief, I explained that 3 weeks ago, Angel approached me and said, will you please give a talk at our seminar? I said, okay, but my work is not in the mainstream of this institute, so I'm afraid it will not be interesting for others. He said, no, it's for younger people, and so, I mean, please do that. And we need to also to teach them that there are other very interesting things other than dynamic symmetry, dynamical systems, and I don't know, topology and other things, which are beautiful, but there are other beautiful things in mathematics. So then I could not reject this idea, so I accepted this invitation. So that's the explanation why I am giving today's seminar. Now, why about this particular topic? Discrete Fourier transform. The point is that I've been doing that last 3 or 4 years already, and I find it interesting, and I enjoy that, doing that. So I decided, so maybe I should tell people that, and to attract their attention to this particular topic. So I hope that I explained almost everything, except that again, taking into account, it's not for people, I don't know, like Carlos, another Carlos, but it's for students. I try to be slow, but I will try to explain everything. Whatever I will say, that all symbols, every full stop, and so on. So, first of all, to talk about discrete Fourier transform, I need to start with actually classical or integral Fourier transform to explain that and to remind you that, if you know something about that, and then go on actually. So, integral Fourier transform. Chalk. His, ¿dónde? Sí, okay. Now I see. Gracias. Oh, yeah. So this is formula, classical formula of integral transform. You have some function f of x, and then you multiply by this factor, which is now normally called kernel of the Fourier transform, this exponential function, and the result gives you another function. So this transformation. Historically, it was introduced by Fourier for the following reason. I will later show that. So it's interesting that if you try to transform derivative of the function, it goes to the multiplication by the variable of the Fourier. I will show you that a little bit later, explicitly. So Fourier idea was that it means that actually Fourier transform transforms differential equation into algebraic one. So his idea, initial idea was that, well, sometimes we cannot solve the differential equation, then we transform that into algebraic, solve it, and then go back, right? And by the way, it's clear from that, so you can invert this transform and can write it back, and then, so I mean, that was the Fourier idea, how to do that. But as it often happens in mathematics and in every science, when you introduce something very useful, and so then later on we understand that it has much deeper actually meaning. So not only to transform differential equation into algebraic, but particularly with the development of the quantum theory. It's not strange, and it's not my idea, but this influenced actually development of the mathematics in general. The point is that I will be mentioning very often quantum mechanics, not because I want, I believe that you know quantum mechanics. You definitely don't know mostly, but please look at that. The reason why I will be showing this parallel, giving this parallel, because quantum mechanics for you should be as beautiful mathematical model. And for the moment we can forget about that. It's applied somewhere. Results of quantum mathematics can be measured experimentally. But it should give you some idea that how these physicists in theoretical physics use pure mathematical things that actually then they measure, right? So, by the way, as far as I know, best university in the world actually, including Moscow State University, as far as I know, some universities I know in the United States, they all at math department, they usually has special courses on which are called quantum mechanics for mathematicians. So it's useful sometimes to see why it's so important. And then actually in quantum mechanics, they observed that you cannot, contrary to classical mechanics, in physics, you cannot measure momentum or velocity and coordinate. To each interpretation of quantum mechanical is that to each of them corresponds some operator, and these two operators do not commute. So commutation relation, I will be using a lot of that. If you have two operators, then you define commutator, which is very simple expression. So this is definition. I emphasize that, right? Bracket on the left defines commutator. If this commutator is equal to 0, then we say that this is, they commute. Why? Why this is important? The point is that the physicists use another pure mathematical statement, actually, for commuting operators. Systems or eigenfunctions are the same. Now I'm mentioning eigenfunctions, and I hope that almost everybody, but still, I remind you, this is definition of the any operator. If you have some rule how to transform one function into another, it means that you define operator. So what are eigenfunctions then? Eigenfunctions are, if you find some function on which action of your operator gives constant multiplied by the same function. So you now understand why I emphasize here definition and here definition of eigenfunctions. And this constant calls eigenvalue. Word eigen taken from German, I don't know why. I mean, at the beginning of the 20th century, contribution of the German scientists into quantum mechanics or in quantum theory was very great, actually. And so they first used that, and then, I mean, in English, writers, scientists accepted that. So eigen, just proper, means proper, meaning the proper. By the way, in Russian there is beautiful word, собственные функции. Some people here know Russian, but, so therefore I'm reminding that. So commuting leads to the system of this. And physicists say that then all those physical quantities which can be measured simultaneously, they correspond to the operators which commute. And this, again, pure mathematical fact, right? It has nothing to do, I mean, with this commutation and system of functions. And I will be using that to define. And now I'm coming to the main question. So you are mathematicians. I wrote you some transformation, and you can check that this defines some operator, right? Which we call Fourier operator. So now, how to find eigenfunction? Sorry, I forgot to mention that why it is important to know eigenfunction operator. So eigenfunctions usually are beautiful characteristics of the operator. Each operator has its own set of eigenfunctions. It's like passport of the operator. And so therefore, it's very, very useful to know eigenfunction. Now, so let us apply that to the Fourier transform. So it defines some linear operator. We can check that. And what are eigenfunctions? So this is question first to students. Then I ask, actually, researchers also, how to find eigenfunctions of this. May I remind you, so probably you know, imagine that here a differential operator, right? So to find eigenfunctions of differential operator arbitrary, it's actually equivalent to solving differential equation, right? Which we know how to do. So in that sense, this is much more or less easy. Now, when you come to the operator written as the integral transform, then how to find? What should we do? I am not asking about details. I will tell you now, actually. But still, can you imagine some way of doing that? Of finding? Anybody? Now I'm asking scientists, researchers, including Carlos, you, how to do that? No, it's not a joke. I'm serious.
Is your operator contracting?
How?
Is your operator contracting?
Otra vez?
Es contractivo. It's contracting. Is this a contracting operator?
Constructing operator. Contracting. What is contracting? I don't know what is contracting operator.
If you have a Banach norm, then it shrinks the norm.
Oh,
Then I can use integration.
you take into account that here are on the whole real line. So it will not be, I am afraid, so easy to use what you suggest actually. Any other idea?
Cesaro averages.
Sorry?
Cesaro averages. They iterate them at Cesaro averages, abril averages, a kind of averages.
Oh, I don't know. Maybe. No, but again, probably I should say that, do you know simplest way of finding actual eigenfunctions? And I will tell you now, sorry?
You can use this
Sorry?
theorem. You can use this theorem to transform multiplication with differential operator. You can.
You are almost coming there, but yes, exactly. But you still not simply express your idea. The idea is simple, actually. One should find some simple differential operator which commutes with Fourier transform, and then using this statement, then solve this simple differential equation, find eigenfunctions, and then this eigenfunction will be exactly eigenfunction of the same Fourier transform. Okay? And again, physicists, particularly in theoretical physics, they use this, almost every day, so to say, right? For them, it is very usual tool, actually, for finding eigenfunction of the complicated operators. Right? So, now, but how to do that? Again, what does it mean to find the differential operator which commutes? Well, very simple. If you now apply operator of differentiation, then you see that what happens here, you differentiate, so it will happen that here, I'm not writing all integral again, it will appear factor variable appears in front of the initial function, right? So then this gives you an idea, but what if now I multiply by that? I just multiply a function by variable, right? And then see what happens here. So, but you can see that actually this will be equivalent to I'm omitting constants like E, I will come back to that. So clearly, if you differentiate kernel by the variable, integration variable, then you will get exactly x here, and x goes up out of the integral, and then this is the relation. Then it means that as a first step, and you can easily, yeah, I forgot to mention, then you integrate by parts that, so you have this expression, right? I'm sorry. So, over R, you integrate by parts and transfer this differential here. Right? Then you will be getting this very important formulas, plus minus over dx, acting on your integral the same r. Now, and here it is important, plus minus I, and then exponential function naturally, and then this, the same expression. Right. So actually I explained that if you take now here linear combination of these two, dx plus or minus x, you will be getting the same here as it written on the blackboard. So you found actually operator. Usually I will later tell you why they are. So this is actually operators A equal to 1 square root. Just I slightly changed normalization, and A dagger is that. So you defined here this, and then in these terms and in operator terms, so we came to the, I prefer still writing this, denoting that operator. So you got this certainly commutation relation that is A plus I, where is that? Which are very important, so-called intertwining relation between operators here of the minus A, F, A, dagger. So this is very important, and I will keep it on the blackboard because later on I will be using that. So you can still, you can tell me, but you were going to find differential operators which commute. But these are very strange relations. They do not commute with Fourier transform. By the way, this is symbolic notation for this integral of Fourier. So they do not commute. They behave very strangely, and just changing order means that you get I and minus I. But actually, we already got the desired result, because now using that you can check if you define another operator which is called number operator, and now number operator which is quadratic in the raising and lowering operators does commute with the Fourier transform. And then it means that, so observe that this product, as you see from here, is just simple differential equation of the second order. You have a lot of experience of solving differential equation, and this can be done easily. And moreover, it turns out that eigenfunctions of the number operator can be explicitly found in in terms of so-called Hermite polynomials. Here, n equal any integer up to infinity. So number of the eigenstates are infinite.
Is this the completed spectrum of?
Sorry?
Is this the completed spectrum? Every eigenvalue is an integer.
So what?
¿Es todo el espectro?
Yes, it's total spectrum of this differential operator, right? And by the way, what happens here, some funny thing actually. Physicists, if they look at that,
There is no continuous spectrum?
there is no what?
Continuum.
Yeah.
No.
Yes.
Okay.
If you write this
The
becomes
second
Laplace plus
equation.
x squared.
Second order equation.
You have some question or remark or?
The number operator, if you write it, it becomes Laplace operator plus x squared.
Divided by what?
If you calculate the number operator, this nx, if you calculate this, becomes Laplace plus x squared, or dx squared plus x squared.
You mean this number operator? It has nothing to do with Laplace. It's Schrödinger operator for the harmonic oscillator.
This is Laplace operator in one dimension.
But for the
Sorry?
It's Laplace operator in one dimension.
dimension 1. Dimension 1, the Schrödinger equation with the Laplace. Laplace in this situation only the second derivative with respect to x.
First, I want to bring to your attention that this is intentionally considered one-dimensional case just for simplicity. Okay? So in that, okay?
Many dimensions will be the Laplace operator. In one dimension is d squared.
Can you please talk louder? I cannot hear what you are saying.
I beg your pardon, I forgot that we are in one dimension.
Okay. Thank you. No, it's okay. I mean, this is seminar, right? I mean, we need to clarify everything. So now, what is funny about that? So we came at the so-called Schrödinger equation for the harmonic linear oscillator in quantum mechanics. So funny is because more or less this could be done before creation quantum mechanics. Fourier transform was known much before. And by just putting this question, what are eigenfunctions of the Fourier transform, you could come to the harmonic oscillator wave function before creation of the notion what is the harmonic oscillator in quantum mechanics.
Natig, is this operator, it's appear before quantum mechanics? This n.
N, of course, N is related with the, it's the same as the Hamiltonian plus 1/2.
In this time,
Sorry?
at this time, there is no Hamiltonian or something like that.
Yeah, I'm intentionally not mentioning Hamiltonian nothing because I did want to emphasize mathematical way of finding eigenfunction of the Fourier transform. It has nothing to do with physics and nothing, okay? So therefore, I wasn't mentioning Hamiltonian at all.
That's right, that this equation, this n, it was called like a Fuchs equation
Sorry?
for dimension 1. Because this operator, this equation, appeared before Heisenberg, before this equation of Heisenberg.
I'm afraid that nobody did that exercise before Heisenberg. pure mathematically.
I remember the name of the Fuchs operator. It was connected with Kleinian groups from in time of studies of monodromy, Kleinian, Fuchsian monodromy.
Okay, maybe you should give reference to me to this work, and I will be very happy to look at it, okay?
No, I don't know really, because I know that for dimension 1, for complex dimension 1, it was connected with monodromy of Fuchsian monodromy. This equation appeared, it was mentioned that for in this situation, this equation is exactly operator of Heisenberg, and so.
Okay. Okay. So now, when more or less everything is clear, I want only to remind you final just remark about Fourier transform. It is well known that force power is just 1. If you apply to the same function 4 times Fourier transform, you will be returning back. So therefore, eigenvalues of the Fourier transform, do not confuse that with the eigenvalues of the number operator, are only 4, which are 4 roots of the 1. So eigenvalues here will be plus minus 1 and plus minus I. So therefore, in this way, when we found also eigenfunctions of the Fourier transform, because number operator commutes with the Fourier transform. So you see only 4 eigenvalues of Fourier transform, which means that each eigenvalue is infinitely degenerate. So, for example, that would be also good. So function f0, f4, and so on. People who like number theory, and they would say that, so you take all function which has index which is equal to 0 modulo 4. Then infinitely many functions will belong to the same eigenvalue. So it's important that this operator, which we found, has distinct eigenvalues for each function. So there is no degeneracy. And therefore, usually eigenfunctions of the Fourier transform can be numbered or ordered by the eigenvalues of the number operator. That's also very important. So that's all about Fourier transform. Now we are going to the discrete version of it. So I don't need that. I keep this. I take out. Yeah, and I don't need that. So what is the discrete Fourier transform? This is discrete Fourier transform, actually represented by the, again, operator, but in the finite dimensional space. So therefore, everybody knows that any linear operator in finite dimension is equivalent to matrix, right? So we know that. So it's explicitly, there is very, very actually do not forget Natig. There is very simple way of exponential here, mn 2 pi I divided by n. And this is the same, exactly the same as just q. It's very convenient to use. So here mn are indices. Here mn are powers of q, where q is defined in a very simple way. It is so-called, actually, we see the cyclic variable because nth power, evidently, of q is just 1. I will need to use that later, so that's important. This is just notation, right? And people who are doing some special functions, of course, can see that some analogy with q parameter which appears in this theory of special functions, but it's here, defined here. So this is the matrix, right? And I sorry?
Mn are bounded.
Peter, thank you very much. Thank you for this question. Of course. So I said that it's matrix in finite dimension, so dimension of this space of n. So, but it's convenient to use this way, starting from 0, but n minus 1. So still the same dimension, but this is more convenient, right? So m and n at finite number. So matrix, before going further, I will speak a little bit about explicit form of this matrix. Because it gives you some idea, actually. One, then it comes 1, q squared, q n minus 1. Here q squared. So if you go this way, then you go again n minus 1. Here 1. And it's not important. I will tell you a little bit later. N minus 1, n minus 1. Sometimes it's called Schur matrix, actually. I will, again, later tell you why it's called Schur matrix. The reason why I wrote explicitly, by the way, you can ask that, well, here everything is very simple. Finite n by n matrix. So what is the problem? Of course, problem of finding eigenvalues and again eigenvectors of this matrix. But this impression is deceptive, actually. It's not so. People, I will just tell you names of Gauss, Cauchy, Dedekind, and some other actual names probably were studying that historically, and Schur was probably more the latest classic who also considered this, studied this matrix. And one beautiful property, I will come to Gauss just a second. If you write sum of the geometric progression So this is the definition of geometric progression, sum of the of this type, and this is formula, right? I hope that everybody remembers, by the way, how to derive this formula for some of this expression. Everybody remembers, right? This is beautiful, actually, a beautiful way of summing this. So you first consider that. That will be Sn minus 1, right? So Sn minus 1 plus Xn minus 1, right? If you group, just consider up to now. But then, so this should be the same as here. Look what happens here. I write it 1 plus X Sn minus 1. Because if you take X out of this part, then you will come again to the same sum, but with number less. But so you have equation for defining Sn minus 1, and you come to this formula. The reason why I am reminding you that is the following. So first of all, if X, by the way, this is takes place for any X. I didn't say what is the X. Even when X is 1, you are getting still. So some looks a little bit suspicious that there is a 0 divided by 0, but you use L'Hopital rules and then you get the same correct result. So it should be n sum, because when X is 1, you see from that, right? So the sum will be n. So whatever. So, but now, if you take that for the cyclic variable, then look what happens here. This will be equal to 1 minus q to the power n. 1 minus q will be 0. Because q to the power n is 1. You know that. So now these matrices have beautiful properties. Except first line or first row, sums of all others rows are equal to 0. I forgot to mention that passage from this row to this row, just you change places of the powers of q. So q are the same as here, as in the sum, but written on another order. So therefore, all rows are equal to 0, except the first one. And all columns are the same. Sums are again 0. Now, another beautiful property of this matrix is that now if you try to evaluate so-called trace of this matrix. Trace is, definition of trace is that simple. Sum of diagonal elements of any matrix, usually called trace. So you evaluate trace of this matrix, and then you see what happens here. It's not important. I will write it in the, so probably I should actually multiply it here in order. It will be actually sum so you see what this sequence, sum, or this sum, or this sequence, the sum of this sequence actually, it's not so easy to find as it was for the geometric progression, because here summation index enters in the square. So that was what attracted Gauss' attention, this type of sums. By the way, he was at that time 19 years old already. So he guessed the result, and then it took him 2 years actually to develop some ways of proving that. And letters of the Gauss in which he actually describes all the situation with Gauss sums are conserved actually, and we have them. So we know that. So, and the answer of that is it's Gauss results. I multiply here, so it's square root out of n. And then here comes 1 plus minus I to power n, and 1 minus I. So this is famous Gauss quadratic sums, and that's the answer for this sum. Okay? And now I'm sure actually use that fact that Gauss sum was not initially related with the discrete Fourier transform. He came to that, to these quadratic sums from in other studies actually. And lately, Schur actually used this fact that trace of this discrete Fourier transform is Gauss sum in order to give another simpler proof of the Gauss results. So, okay, I almost actually finished. Yeah, very good. So I'm still in time, right? More or less. And now you would be surprised if I tell you that this simple problem of finding eigenvectors and so you have here vector z, you have here vector y, and then, so this is discrete Fourier transform. These vectors, they have, I will write here, components naturally, z0 and so on, zn minus 1. So this is the definition of discrete Fourier transform. You have any finite sequence defined by this number n. By the way, number from the can be any integer number. It's clear, right, from the beginning, and it may vary actually. And so this is definition of the transform, discrete Fourier transform. And the point is that now what are actually eigenvectors or here n equal from 0 to n minus 1. So this is equal to lambda k and you so you will be actually surprised if I tell you, although I mention great names, I mentioned that so many years passed from the time when we started to study. They are not known. We don't know explicit form of for any arbitrary n. So what we are doing and what I don't have much time now to speak about what we've done actually. We actually constructed explicitly difference, not differential, difference operators, which, yes, it's here, which satisfy the same, here, it was here, the same intertwining relation with the discrete Fourier transform. Then we defined discrete number operator where n is defined as this type of product explicitly. And then all this problem now is reduced to the solving difference equation. So as check for that our idea is correct, we made this calculation. We took n equal to 5 and tried to see that everything is correct. And so result is absolutely beautiful. You get exactly we got 5 discrete eigenvalues for this difference operator. And now we are working actually for the last step, exactly finding explicit form of the eigenvectors for this discrete operator for arbitrary n. This is not done yet. So that's all. I will stop here and I will be happy to answer your questions.
What motivated to define the discrete function of the Fourier transform in this way?
Okay, right. No, yeah, absolutely good question. And you see, you can analytically prove that when n tends to infinity, you reproduce actually continuous result. So therefore, it was thought of as the discretization of the continuous case, or the. So yeah, you know that sometimes it's when you consider finite systems, then you don't have whole real line. So everything is concentrated on the finite interval. So you need actually to define discrete version of the Fourier transform, right? In order to work with the system. So, and originally people, creators of that, they said that this is a discrete version of the classical integral. Okay. Needless to say, related with your question, that when you discretize, you lose this continuity, and then you don't have any more differential operators. So everything goes to the difference operators, finite differences. So therefore, complication. Although I said that at the beginning, matrix is simple, right? N by N matrix. So what is the difficulty? The difficulty is that you cannot use apparatus of the real analysis. You cannot differentiate. You cannot. So therefore, it's still difficult. You see, although seemingly it's easy. I mean, it's simple. I feel that you have some question. Don't ask Piotr, ask me. So why? I mean, no, Piotr definitely knows more than I do, but I mean, I will be happy.
I show you.
This is very related to summation methods.
To what?
Summation methods.
Summation?
Summation methods. And it is. So there are summation methods which are built out of matrices.
Uh-huh.
So-called Holder method for summation. And there's also a method which is takes hours.
No, that is not
This
Hilbert
abril.
method.
But why nobody used this? You mentioned some method. Why nobody used to find the explicit form of these eigenvectors?
It was used, for example, the Gauss used the abril summation formulas. The abril
No. Okay. But Gauss used and to define some his Gauss result we can use in order to know how trace behaves, but it doesn't give me a possibility to find eigenvectors. This problem is different.
I show you now that this book. There exists a kind, not definitively, but there exists a way to find a fixed point, not as the eigenvalue, but the fixed point.
Why I need this fixed point?
Fixed point is the kind of eigenvalue.
Okay.
Fixed point is eigenvalue is 1,
Yeah.
and if you have the root unity,
Okay.
the point spectrum belongs to the root unity. That means that.
So you claim actually you know how to define eigenvector? No?
No, I cannot solve this one. This is really very difficult thing.
Okay. Piotr, otherwise the result would be published, right? I mean, appeared, right?
But there exist a ways, in general one, action of operators on a small spaces or conversion space of conversion sequences, or space of full sequences with special norms which allow to receive a partial result. Not everything. And another
But here, Piotr, I don't understand one thing. In order to know norms, you need to know eigenvectors. So I mean, so then it's the same problem. What was first, egg or hen, right? So I mean, so what to start with what? I mean, and to solve what? Okay. Anyway, maybe we will talk about that. Piotr, we definitely will talk about that later. Any other question? No? I had a teacher in analysis, and when he finished his lecture on analysis, he was very good. I mean, so whatever I know, I'm thanks to him. So he was angry. He was asking, "Are there questions?" Everybody, nobody asked it, and he said, "You are stupid. You didn't understand anything. So therefore, there are no questions." So I hope that this is not the case here. Definitely. So, but somehow it reminded me. Thanks. Thank you.